Then I would like to talk about the chemical composition by use of catalytic dehydrogenation of two compounds. And we have utilized some energy abundantly on the Earth, such as solar heat, geothermal heat, and thermal electricity. It is because their temperature are too low. Utilization of low quality heat is important to the environmentally regulating life. In order to rise the temperature, no mechanical compression is required in these heat-form systems. Our system features has the following peculiar and advantageous features in contrast to regular type, absorption type, and regular type system. Firstly, this system is operated under common pressure. Secondly, the extent of temperature rise is amount to 100 centimeters. And thirdly, the both continuous operation and energy storing use is possible. Recently, chemical system has attracted peculiar interest because the extent of temperature rise is large. And secondly, thermal energy can be transported and stored. In this presentation, I would like to propose a new chemical system which adopts a reversible reaction couple of two-proton dehydrogenation and acetone hydrogenation. The standard release energy change of some hydrogenation and the dehydrogenation couples are shown here. These are the boiling point. These are the final temperature, which will fix the energy level become zero. The boiling point usually lower than the final temperature. And the boiling and reflux conditions, the hydrogenation of two propanols proceed because the product hydrogen is immediately expelled out from the reaction medium. And the never come back. On the other hand, acetone hydrogenation is thermodynamically favorable time temperature. That is 100, 202 centigrade, which much higher than the boiling temperature of the two-propanol acetone is solution. In this present chemical system, the role of catalytic dehydrogenation of two-propanol is most important because it enzyme reaction converts the low quality heat into the chemical energy. This is process of this chemical system. It is composed of enzyme reactor RL, distillation current D, and exocyte reactor RH. Liquid phase dehydrogenation of two-propanol proceed at 80 centimeters, where the low quality heat converted into heat of reaction and evaporation. Gases acetone hydrogenation proceed at 200 centigrade. Separation of acetone and hydrogen from two-propanol is achieved by cooling assertively. Our experiment on catalytic to propanol dehydrogenation was carried and followed. Solid catalyst was suspended in 2-propanol and heated under boiling condition. The evaporated gas passed through a reflux condenser and cooled into correct into a gas burette at atmospheric pressure. Gases and liquid phase components were analyzed by gas chromatograph using active carbon and PET currents respectively. The carbon-supported lithium, rhodium, platinum, and pyrogen catalysts were used for 2-propanol dehydrogenation in suspended state and the boiling and reflux condition. Excludes formation of hydrogen and acetal were confirmed in the liquid phase and gas phase components respectively. The rate introduction caused by acetone were confirmed by this Randomir type equation, which gave a straight line each other. We used four kinds of 2-propanol. The figure shows the position of deuterium. OD is here, 2D is here. DH is O. The activity order over the catalyst were lithium, rhodium, platinum for 2-propanol dehydrogenation. It is to be noted that the rate of deuterium substituted to propanol were different order from metal to metal. The kinetic isotope effects of 2-propanol dehydrogenation are summarized as follows, as shown here. With about rhodium, platinum, catalyst, deuterium isotope effects were larger for making hydrogen than the hydrogen bond, suggesting the dissociation of making CH bond dissociation is rate retarding. On the contrary, the same step was done for the lithium catalyst, since the isotopic effect for making hydrogen was smaller than for hydrogen bond. The deuterium distribution in molecular hydrogen were different from metal to metal also. The leucine gave a reasonable distribution among H2, HD, and D2 from 2-propanol to D. However, a large quantity of HD instead of HD and D2 was formed from the surface of platinum or rhodium catalyst. This scheme shows the reaction mechanism over the platinum catalyst. When the amount of 2-peroxide and hydrogen species H will be supplied to platinum surfaces by passive dissociation of 2-propanol hydroxyl group. As the CH bond dissociation step is rate retarding on the surfaces, acetone After acetone is dissolved into the liquid phase, molecular hydrogen is formed from the surface hydrogen free, which leads to the limited content of deuterium in the molecular hydrogen. When the mixture of 2-propanol and 5% acetone D6 was reduced with a catalyst, hydrogen was evolved at diminished rate. It was found for the Hussein catalyst that the deuterium atoms of acetone were transferred exclusively to the methyl group of 2-propanol, while the hydroxyl and methyl group remain without any Hd exchange. After the first reaction, 88% of deuterium in acetone was converted into the methyl group of 2-propanol. It was deduced, therefore, that the hydrogen transfer from surface hydrogen species to deuterium substituted acetone proceeds rapidly over the Hussein catalyst under the condition of 2-propanol dehydrogenation. The rate of hydrogen evolution from 2-propanol and hydrogen transfer from 2-propanol to acetone were compared with respect to the Hussein catalyst. The rate of hydrogen transfer from 2-propanol to acetone D6 was obtained as 4.65 millimole per hour, was 7.55 times larger than that of hydrogen evolution, 0.65. The passive processes in 2-propanol dehydrogenation of glycerin, platinum, and rhodium catalyst are summarized in this scheme. As for the platinum and rhodium catalyst, the formation and dissolution processes of molecular hydrogen was passive. While the CH bond is splitting and its reverse processes are passive for glutamine. Predominant catalytic activity of glutamine in 2-propanol dehydrogenation would be ascribed to its efficiency in the CH bond dissociation. The passive CH bond dissociation over glutamine and the passive hydrogen evolution over the platinum or rhodium were intended to combine with each other to exert a significant effect. We attempt by this reason to prepare a metal composite catalyst by co-absorption and sodium chlorhydride reduction for the chloride mixture from the active carbon support from the aqueous solution. The catalytic activity of 2-propanol dehydrogenation was obviously improved by adopting the metal composite. This is then photographed and conventional analysis of the carbon-supported lithium platinum composite catalyst. Each part will contain both lithium, platinum, respectively. Part 1 and 3 were combined to be a single crystal. As the engaged enlarged image of part 1 shows, the lithium platinum metals is known as a single crystal. The Cherry model is not appropriate for its carbon-supported composite catalyst. Various kinds of suspended storage catalysts have been investigated for two-proton dehydrogenation so far. And the linear type equation describes the three-phase dehydrogenation of two-proton. Well, among the single and component catalysts, the activity of lithium is the highest, which was enhanced by adding platinum as a component. The surface modification with a metal component, such as this acetyl platinum, which includes carbon. As for the hydrogen product producing catalysts, further improvement to attain high space time yield and low production product utilization is anticipated for the sake of designing a more compact and highly efficient system. Last year, JH company and Japanese chemical engineering company constructed a pilot plant for this system in Atomic Technology Center under financial support by NITEDO, New Energy Development Organization of MITI in Japan. This is overall formula for the experimental apparatus of two-proton acetyl nitrogen chemical control system. This is the backside photo. This is an experimental apparatus for the liquid phase dehydrogenation of two-proton. This is Masaru. And this is the experimental apparatus for the liquid gas phase dehydrogenation of acetone. Thank you very much for your attention.
Thank you, Doctor. Questions or comment, please?
Al Van Ice, Penn State. Is this working? Is this? Van Ice, Penn State. I was wondering, in regard to the dehydrogenation reaction, did you by any chance put any of these metals on titanium?
Titanium?
Yes, because titania definitely increases the rate of acetone hydrogenation with platinum. And it's interesting that these same catalyst systems have not been studied often for the dehydration reactions. But there's a possibility that the rate for dehydrogenation might also be higher. And you might get more active catalysts putting them on titania than putting them on carbon.
I tried to some kind of catalyst for this reaction, but I think this catalyst is better.
This is better?
Yes, better. I try to many kind of patterns, but
Including titanium?
yes, yes.
Okay, good.
Local Japanese company try to many kind of this reaction by use of many kind of patterns, but this is best one, I think.
Other next question? Please.
Your one shows that the alumination with the helium substitute open up is always lower than the unliquid structure. Your one of your paper shows that all the different samples, the iron is lower than unlimited sample. The unlimited sample sometimes the triangular, that is the second carbon atom is different, and that's true of the curve. The second carbon atom different sample is the slowest for hydrogen evolution. Whereas